Welcome to this coding session. In this video, we'll tackle LeetCode problem number 1049, last stone weight 2. This is an exciting dynamic programming problem that challenges us to minimize the difference between the weights of two subsets. Let's dive in and explore the problem step by step. In this problem, we are playing a game with stones, where each stone has a specific weight given in an array called stones. On each turn, we pick two stones, smash them together, and depending on their weights, we either destroy both stones or create a new stone with a reduced weight. Specifically, if the weights of the two stones are equal, both are destroyed. However, if the weights are different, the smaller stone is destroyed, and the larger one is reduced by the weight of the smaller stone. This process continues until there is either one stone left or no stones at all. The goal is to determine the smallest possible weight of the last stone left, or return 0 if all stones are destroyed. The input is an array stones where each element represents the weight of a stone, and the output is an integer representing this smallest possible weight. Now, let's look at an example to understand the problem better. Suppose the input array is stones equals 2, 7, 4, 1, 8, 1. The optimal way to smash the stones is as follows. First, we smash the two heaviest stones, which are 7 and 8. Since their weights are different, the smaller stone, 7, is destroyed, and the larger stone, 8, is reduced to 8, 7 equals 1. Now the remaining stones are 2, 4, 1, 1, 1. Next, we smash the stones with weights 2 and 4. The smaller stone, 2, is destroyed, and the larger one is reduced to 4, 2 equals 2. The remaining stones are now 2, 1, 1, 1. Continuing this process, we smash the next two stones, which are 2 and 1. Here, the stone with weight 1 is destroyed, and the larger one is reduced to 2, 1 equals 1. The remaining stones are 1, 1, 1. Finally, we smash the stones with weights 1 and 1. Since their weights are equal, both stones are destroyed, leaving us with just one stone of weight 1. Therefore, the smallest possible weight of the last stone is 1. Let's look at another example. Suppose the input array is stones equals 31, 26, 33, 21, 40. Again, we follow the same process. First, we smash the two heaviest stones, which are 40 and 33. Since their weights differ, the smaller stone, 33, is destroyed, and the larger one is reduced to 40. 33 equals 7. The remaining stones are 31, 26, 21, 7. Next, we smash the stones with weights 31 and 26. The smaller stone is destroyed, and the larger one is reduced to 31, 26 equals 5. The remaining stones are now 5, 21, 7. Then, we smash the stones with weights 21 and 7. The result is a new stone with weight 21, 7 equals 14. The stones left are 14, 5. Finally, we smash the stones with weights 14 and 5. The smaller stone is destroyed, and the larger one is reduced to 14, 5 equals 9. This leaves us with one stone of weight 9. Hence, the smallest possible weight of the last stone in this case is 5. Let's consider one more example with a smaller array. If the input is stones equals 1, 2, we smash the two stones with weights 2 and 1. Since the weights differ, the smaller stone, 1, is destroyed, and the larger one is reduced to 2, 1 equals 1. The remaining stones contain just one stone with weight 1. Therefore, the smallest possible weight of the last stone is 1. Now, let's review some constraints and edge cases. The input array can have a length of up to 30, and each stone has a weight between 1 and 100. For edge cases, if there is only one stone, the result is simply its weight. If all stones have the same weight, they will completely cancel each other out, leaving no stones at the end. For small weights, like 1, 1, 1, 1, the final result will also be 0 because the stones will all cancel out in pairs. These considerations are important for building an optimal solution. To begin addressing this problem, we can think about it in terms of dividing the stones into two subsets such that the absolute difference of their sums is minimized. A straightforward way to approach this is by using a brute force method where we generate all possible subsets of the array. For each subset, we calculate the sum and determine the minimum absolute difference between the two subsets' sums. This method is simple to conceptualize, as it systematically examines all possible groupings. However, the problem is that generating all subsets has an exponential time complexity of O(2 to the power of n, where n is the number of stones. This means that for even moderately sized inputs, the computation becomes infeasible. Therefore, while this approach helps us understand the problem, it's not practical for larger datasets due to its inefficiency. We need something significantly faster. Now, a more efficient solution can be developed using dynamic programming. By reframing the problem, we see that it's a variation of the partition equals subset sum problem. Here's the idea: if we calculate the total weight S of all the stones, the goal becomes finding the maximum subset sum, S1, that is less than or equal to S divided by 2. Once we have S1, the answer is simply S minus twice S1, representing the weight difference between the two subsets. To achieve this, we use a dynamic programming array where dp, j, indicates whether a subset sum of j is achievable using the given stones. As we iterate through the stones, we update this array to reflect all possible sums we can form. This approach is much faster because it avoids manually generating subsets and instead uses the structure of the problem to efficiently compute the result. The time complexity is O(n*(s), where n is the number of stones and s is the total weight, and the space complexity is O(s), making this approach feasible for reasonably large inputs. An alternative solution could be using a greedy strategy, where we repeatedly smash the two heaviest stones together and reduce the problem size. While this might seem efficient, there's a critical issue: it focuses only on local decisions, which means it doesn't guarantee the global minimum difference. For instance, smashing the heaviest stones first might result in a poor final configuration that doesn't minimize the difference. As a result, this approach is fast but unreliable, as it doesn't account for all possible combinations of subsets. Therefore, while it might work in some cases, it cannot ensure correctness for all inputs, which makes it unsuitable for solving this problem comprehensively. Instead, the dynamic programming approach emerges as the most suitable strategy, balancing efficiency and accuracy. When choosing the dynamic programming approach, it's important to recognize the trade-offs. The primary downside is that it requires space proportional to the total weight of the stones, S, since we maintain a DP array of that size. However, this is a reasonable trade-off when compared to the exponential time complexity of the brute force method or the correctness issues of the greedy approach. The DP approach offers a manageable time complexity of O(n*(s), and guarantees accurate results by systematically exploring all achievable subset sums. This makes it the ideal choice for solving this problem. The key insight that unlocked this solution was recognizing the problem as a variation of the partition equals subset sum problem, which allowed us to leverage existing techniques and adapt them effectively. With this, we achieve a balance of efficiency, correctness, and simplicity, providing a robust solution to the problem. The problem asks us to partition an array of stones, where each stone has a specific weight, into two subsets such that the absolute difference between the sums of the subsets is as small as possible. This is a variation of the classic partition problem, which is widely studied in computer science. To solve this, one potential approach is the brute force method. This involves generating all possible subsets of the stones array. Using recursion or bit masking, we can systematically create every subset. If the array has n stones, there will be 2n subsets, as each stone can either be included in a subset or excluded. Each subset represents one way to partition the stones, and this will form the basis of our exploration in solving the problem. Once we have generated all the subsets, the next step is to calculate the complement subsets. For a given subset, let's call it sum S1. The complement subset would include the stones not in the current subset, and its sum would be S2, calculated as total sum S1. Here, total sum is simply the sum of all elements in the array. After determining the sums of both subsets, we compute the absolute difference between them, represented as abs, S1, S2. This difference tells us how imbalanced the current partition is. To find the optimal solution, we maintain a variable min difference initialized to infinity. As we iterate through the subsets, we continuously update min difference if we find a smaller absolute difference. Finally, after evaluating all subsets, the value of min difference is returned as the result, representing the smallest possible difference. When working with the brute force approach, there are a few critical insights to consider. First, generating all subsets is computationally feasible only for small input sizes. With n stones, the time complexity is exponential at 2 to the power of n, which makes this method impractical for large n. Second, the symmetry of subsets plays a role in reducing redundant calculations. For example, the subset A, B, and its complement C, D produce the same absolute difference as C, D, and its complement A, B. By recognizing this symmetry, we can optimize the algorithm by focusing only on subsets up to half the array size. Additionally, an important optimization is early stopping. If at any point we calculate an absolute difference of 0, we can terminate the algorithm immediately, as this is the minimum possible difference. To implement the brute force algorithm, we rely on specific data structures and variables. Subsets can be generated and stored using a list or set, which allows us to systematically explore different groupings of stones. Key variables include min difference, which keeps track of the smallest absolute difference encountered, and total sum, which is the pre-computed sum of all elements in the stones array. This pre-computation allows us to calculate the complement subset sum S2 quickly during each iteration. In terms of complexity, generating all subsets takes 2 to the power of n, and calculating the sum for each subset takes n. As a result, the overall time complexity is n*2 to the power of n. Space complexity is also significant, as storing all subsets requires 2 to the power of n space in the worst case. Several edge cases must be considered to ensure the robustness of the solution. For example, if there is only one stone in the array, it is impossible to partition it into two subsets, so the output is simply the weight of the stone itself. If all stones have equal weights, the absolute difference between the two subsets will always be 0, since they can be perfectly divided. An empty array is another edge case, where the result is trivially 0 because no stones are present to partition. Lastly, while the algorithm handles large weights correctly, the exponential time complexity becomes a limiting factor as the size of the input array grows, making it computationally infeasible for large values of n. To understand the brute force approach better, let's walk through an example. Suppose the input array is stones equals 2, 7, 4, 1, 8, 1. The total sum of all stones is 23. The first step is to generate all possible subsets of the array. Some example subsets include 2, 7, 2, 7, and 2, 7, 4, 1, 8, 1. For each subset, we calculate its sum, S1, and the sum of its complement, S2 equals total sum S1. Then, we compute the absolute difference abs, S1, S2. For instance, with the subset 2, 7, 4, S1 is 13, S2 is 10, and the difference is 3. As we iterate through all subsets, we track the smallest difference found. In this case, the minimum difference across all partitions is 1, which becomes the final result. While the brute force approach is straightforward, it is inefficient for larger inputs due to its exponential complexity. A more efficient solution involves dynamic programming. Using a DP-based knapsack approach, we can explore valid partitions without explicitly generating all subsets. This drastically reduces the time complexity to n* total sum, where total sum is the sum of all stones. By leveraging the properties of the problem and focusing only on feasible partitions, dynamic programming allows us to handle much larger inputs efficiently while still achieving the same result. This solution uses a dynamic programming approach to solve the problem of minimizing the weight difference between two subsets of stones. The algorithm starts by calculating the total weight of all stones, total_sum, and defining a target weight as half of this total. The idea is to find the closest possible sum to the target using a subset of stones. The dynamic programming array DP is initialized to store the maximum weight achievable for each capacity up to the target. The outer loop iterates through each stone, and the inner loop iterates backward through possible capacities from the target down to the current stone's weight. This backward iteration ensures that each stone is only considered once. For each capacity j, the value of dp, j, is updated to be the maximum of its current value or the sum of the current stone and the value of dp, j, stone. This step ensures that we consider the inclusion of the current stone in the subset. Finally, the result is calculated as the difference between the total weight of all stones and twice the closest sum to the target, stored in dp, target. This difference represents the minimal possible weight difference between the two subsets. This approach is efficient, with a time complexity of n*target, where n is the number of stones and target is half the total weight, and a space complexity of O, target. It effectively handles the constraints and edge cases of the problem. This is the Java implementation of the last stone weight 2 problem from LeetCode. The solution uses dynamic programming to determine the smallest possible weight difference when the stones are smashed. The logic mirrors the Python implementation, with differences in type declarations and the use of Java's array-based dynamic programming approach. The DP array keeps track of the closest sum achievable to half of the total weight, and the result is derived from the difference between the total sum and twice this closest sum. To solve this problem, we start by analyzing the input array of stones, which is 2, 7, 4, 1, 8, 1. First, we calculate the total sum of all the stones, which is 23. Our goal is to split the stones into two groups such that the difference between their sums is minimized. To achieve this, we aim to find the closest possible sum to half of the total sum, which is 11. For this, we use a dynamic programming approach. We initialize a DP array of size target plus 1, filled with zeros. This array will help us track the maximum achievable sum for each capacity from 0 to the target. Now, we process each stone one by one. Starting with the stone of weight 2, we iterate backward from the target, 11, to 2. The value at DP, 2, is updated to 2 because it represents the maximum sum we can achieve with this stone. Similarly, when we process the stone of weight 7, the value at DP, 7, is updated to 7. This represents the maximum sum achievable with the first two stones. The DP array is updated accordingly after processing each stone. Next, we process the stone of weight 4. Iterating backward, we update DP, 11, to 11 because we can now achieve this sum by including stones that add up to 11. At DP, 6, we update its value to 6, representing the maximum sum achievable with this stone. After processing all the stones, our DP array is finalized, and it contains the maximum sums we can achieve for each capacity up to the target. The value at DP, 11, is 11, which is the closest we can get to the target. To compute the result, we subtract twice this value from the total sum. This gives us 23 minus 2 times 11, resulting in a difference of 1. Thus, the output for this example is 1. This approach ensures that we minimize the weight difference between the two groups of stones. Now, let's look at another example with the input 31, 26, 33, 21, 40. The total sum of these stones is 151, and our target is half of this value, which is 75. We initialize a DP array of size 76, filled with zeros. Starting with the first stone of weight 31, we iterate backward from 75 to 31, updating the DP array to reflect the maximum achievable sums that include this stone. Similarly, we process the remaining stones, 26, 33, 21, and 40, one by one. For each stone, we iterate backward from the current target, updating the DP array to include the impact of that stone. By the end of this process, the DP array represents the maximum sums achievable for each capacity up to the target, considering all the stones. After processing all the stones, the value at DP, 75, gives us the closest sum to the target that we can achieve. To calculate the result, we subtract twice this value from the total sum. This gives us the minimum possible difference between the two groups of stones. For this example, the result is computed as the total sum, 151, minus 2 times the value at DP, 75. This difference represents the smallest possible weight imbalance, and the final output is derived from this calculation. Now, let's consider a simpler example with just two stones, 1, 2. The total sum here is 3, and the target is 1. The DP array is initialized with two elements, both set to 0. For the first stone of weight 1, we update DP, 1, to 1, representing the maximum sum achievable with this stone. For the second stone of weight 2, we attempt to update DP, 1, again, but no change is needed since the target is already achieved with the first stone. The final DP array remains 0, 1. To compute the result, we subtract twice the value at DP, target, from the total sum. In this case, the result is 3 minus 2 times 1, which equals 1. Therefore, the output for this example is also 1. This demonstrates how the dynamic programming approach can handle both complex and simple inputs efficiently, always finding the minimum possible weight difference. To analyze the time complexity, we start with the initialization step. Here, we calculate the total sum of all stone weights, denoted as total_sum, and determine the target, which is half of this total. Since summing up the elements in the array involves iterating through all n stones, this step takes n time. Next, we update the dynamic programming table. The DP array has a size proportional to target plus 1, which translates to total_sum/2. For each stone, the outer loop runs n times, while the inner loop iterates from target down to the weight of the current stone. In the worst case, this inner loop runs total_sum/2 times for each stone. Combining the iterations of both loops, the total time complexity for updating the DP array becomes total_sum/2. When we add the initialization step, the overall time complexity of the solution is determined by these operations. Simplifying the time complexity further, we combine the terms n and total_sum/2. Since the summation of stone weights, or total_sum, dominates for larger inputs, the time complexity simplifies to total_sum. Now, turning to space complexity, the primary contributor is the DP array, which is initialized with a size of target plus 1, or total_sum/2. Besides this, the algorithm only uses a few scalar variables, such as total_sum and target, which require constant space, or 1. Therefore, the overall space complexity is dictated by the size of the DP array, resulting in total_sum/2. To put the efficiency of the dynamic programming solution into perspective, let's compare it to a brute force approach. A naive method would involve generating all possible subsets of the stones array and calculating their sums to find the closest value to total_sum/2. This process would require exponential time, specifically 2 to the power of n, since there are 2 to the power of n possible subsets for an array of size n. The space complexity in this case would also be 2 to the power of n, as we would need to store all subsets. In contrast, the dynamic programming approach reduces the time complexity dramatically to total_sum, and the space complexity to total_sum/2. This makes it much more scalable for larger inputs. Whether in the best, worst, or average case, the time complexity remains total_sum, because every stone is always processed, and the DP table is fully updated. Breaking down the mathematical reasoning for the big O analysis, the outer loop in the dynamic programming approach runs n times, iterating once for each stone. The inner loop runs target times, where target is equal to total_sum/2. Therefore, the nested loop requires total_sum/2 operations, which simplifies to total_sum. On the space side, the primary factor is the DP array, whose size is proportional to total_sum/2, resulting in a space complexity of total_sum. In conclusion, the dynamic programming solution offers a polynomial time complexity that is significantly more efficient than the exponential time complexity of a brute force approach, making it highly practical for solving this problem. When working on this problem, there are several common mistakes that can trip you up if you're not careful. First, it's easy to ignore the constraints, but these play a critical role in shaping the solution. For instance, with 1 = n = 30 n sum stones equals 10⁻⁴, a brute force approach might seem feasible at a glance, but its exponential time complexity makes it impractical. Understanding the constraints helps you narrow down the right approach. Another mistake is confusing this with a standard subset sum problem. While both involve subsets, here the goal is to minimize the difference between two subset sums, which requires a slightly different mindset and strategy. Finally, edge cases are often overlooked. For example, with a single stone array like 1, the minimum difference is just the weight of that stone. Arrays with identical values, such as 5, 5, 5, 5, test your solution's ability to handle even splits. And for large sums near 10⁻⁴, you need to ensure your solution handles potential integer overflow, especially in languages with fixed integer sizes like C++ or Java. Another area where mistakes frequently occur is in the dynamic programming state transitions. If you're using a DP array, updating it in the wrong order, like iterating forward instead of backward, can overwrite states prematurely, leading to incorrect results. This is a critical detail to get right. Inefficient backtracking is another pitfall. Without memoization, recursive brute force approaches lead to redundant calculations, making them infeasible for larger inputs. From an interview perspective, recognizing the pattern is key. This problem is a variation of the partition equals subset sum problem, so being able to connect the dots shows strong problem-solving skills. While it's fine to start with a brute force solution to explain your thought process, you should quickly shift to a dynamic programming approach for efficiency. Also, be prepared to discuss trade-offs, such as the time-space differences between recursive DP with memoization and iterative DP. Finally, always mention how you've accounted for edge cases, like arrays with one element, all zeros, or very large sums. This demonstrates attention to detail and robustness in your solution. Once you understand the nuances of this problem, exploring related problems can deepen your understanding. For example, LeetCode 416, partition equals subset sum, is highly relevant, as it shares a similar structure. Other related problems include LeetCode 494, target sum, and LeetCode 698, partition to k equals some subsets. These provide opportunities to practice similar strategies in different contexts. Now, in terms of alternative approaches, recursive backtracking is one option. This involves exploring all possible subsets, calculating the difference between their sums. While straightforward to implement, it has exponential time complexity, 2 to the power of n, which makes it impractical for larger inputs. Another option is using a 2D dynamic programming array. In this approach, DP I(j) tracks whether a sum j can be formed using the first I stones. While effective, the time complexity of n*sum stones and space complexity of n*sum stones can become prohibitive for larger sums or inputs. It's important to weigh the trade-offs of these approaches depending on the specific problem constraints. A more optimized approach is to use dynamic programming with a 1D array. This reduces the space complexity to sum stones by maintaining only the current state, rather than a full 2D table. However, you need to be careful with state updates to avoid overwriting values prematurely, which requires iterating backward through the DP array during updates. Another alternative is using a greedy heuristic. For instance, you might try partitioning the stones iteratively based on a largest first strategy. While this can be faster and easier to implement, it doesn't guarantee the optimal solution and may fail to meet the exact requirements of this problem. In summary, choosing the right approach, whether it's DP, recursive backtracking, or a heuristic, depends on balancing efficiency, accuracy, and the constraints given in the problem. Great job! To summarize, we tackled last stone weight 2 using dynamic programming to solve a subset sum variation. Remember the key takeaways, and use this approach in similar optimization problems. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!